Okay, for problem 7.71, we have a common source configuration, so a common source configuration, which means that this source here is grounded. So this is VGS, so this is gate, this is source, so it's, well, if you like, we could draw this way here. Let me just erase this stuff here. So here's the source, and it's grounded. Okay, that's a common source configuration. So we know that for this particular configuration, GM is actually 5 milliamperes per volt. Now, if we insert a source resistance, so suppose we remove this ground here and put a resistor, RS here, we verify the transconductance, the effective transconductance of this circuit, it changes to 2 milliamperes per volt. Okay, so that's what's happening. That's what the problem is telling us. But now let's first focus on the common source configuration. Okay, now we know that ID1, so this ID1 here, okay, is equals to GM times VGS1, right? That's this current here. So if we isolate ID1 divided by VGS1, that's actually our transconductance, right? So nothing wrong with this fact here. So we are basically defining that our transconductance is this ratio between a current and a VGS. Now, if you look at this particular circuit here, VGS is actually this signal, right? So we can rewrite this equation here by changing this VGS1 here to this signal. And that's our first transconductance, which is 5 milliamperes per volts. Okay, so that's that's our first analysis. Fine. Now, if we insert the source resistance, we no longer have that ID1 because on the previous circuit we were taking VGS1 as the difference between the gate, the potential at the gate, and the source that was grounded. So the source was 0. But now, because this ID here, so this ID here is flowing through the ground, it actually creates a voltage drop across this RS. So now our VGS2 is actually VG minus BS, which is here. So VGS2 is actually, so VG here, it's just this signal, right? Because here's the gate, so it's connected directly to the gate. So this is equals to this signal minus, now what's the value of, so the value of the current that's flowing through this RS is actually GM times VGS2. So it's RS times GM, our previous GM, okay, times VGS2. Okay? And this ID2 is equals to GM times VGS2, that's equals to ID2 this is ID2, which is equals to GM times VGS2, which is this signal minus RS ID2. So if we isolate ID2 here, minus GM RS ID2, so sorry, it's plus because it's minus here, so it goes to the right, to the left hand side here. That's equals to GM this signal. And if we isolate ID2 here, this is 1 plus GM RS, that's equals to GM this signal. If we isolate ID2 divided by this signal, that's equals to our GM2, or the effective transconductance, is equals to the current transconductance divided by 1 plus GM RS. And that's the equation that we are interested. Okay, because we know that this GM2 is equals to 2 milliamperes per volt, and we know that GM is actually 5 milliamperes per volt. So if we know those two values here, we can determine RS. If we isolate RS in that equation, okay, we get that GM minus GM2 divided by GM2 times GM1. So our RS is equals to 5 milliamperes per volt minus 2 milliamperes per volt divided by 5 milliamperes per volt times 2 milliamperes per volt, which gives us an RS that's equals to 300 ohms. Okay, so I think well, it might be like confusing, but let me summarize here. So first we analyze we got this relationship. So if we have like ID1, okay, in this first analysis, ID1 divided by V signal, that's our first transconductance. So that 5 milliamps per volt without the source resistance. Okay, that's GM. Now once we inserted this RS here, we basically change VGS, because VGS is the potential difference, so it's the potential between VG and Vs. On the previous circuit it was 0 because the source was grounded. Now it's no longer 0. We have some substantial Vs here that's equals to that ID2 times Rs. And that's what we have done here. So first we've equate VGS2, which is VG minus Vs, and that's basically Vg is the signal, Vg minus Rs, so Vs is Rs times ID2. That's what we have here. Now, we know that ID2 is equals to Gm because this Gm here, it didn't change, right? It keeps, Gm keeps the same. What's changing is VGS2 in this analysis. So we just wrote that ID2, this new current, is Gm times VGS2. And if we substitute this equation for VGS2 inside this equation for ID2, we start to get this ID2 in common here. And we can isolate ID2 over V signal, which is the effective transconductance that we perceive once we insert this series resistance. So not this series, this source resistance. Okay, and this ID2 over V signal is our effective transconductance. That equals to the previous conductance, so this 5 that we had, divided by 1 plus Gm times the source resistance. And that gives us that to keep that effective transconductance of 2 milliamperes per volt, we should insert a source resistance of 300 ohms.